Good morning, everyone. Thank you for joining Megger webinar. I'm Grace. I'm the marketing manager for Megger East Asia, and I'll be the moderator today. Today is a live webinar. You're automatically muted to prevent any background noises. During the webinar, if you have any questions, please type into the question box, which you can see on the left of your screen. We'll answer your questions at the Q&A session. At the end of the webinar, please have us fill in the survey, which you can see on the right-hand side. We'll be sending the presentation materials to those completed the survey. You'll be able to download an attendance certificate after you have finished the webinar and completed the survey. And the recording of this webinar will be sent to you in 2 days' time by email. Today, our topic is live streaming of insulation resistance test, analyzing resistance and current graph. Next slide, please. Our presenter today is Mr. Michael Evangelista, who is our Megger East Asia Technical Support Group leader. He started with Megger in 2016 as application engineer. He has a broad experience in different electrical applications and is appointed as the product champion for transformer testing. Michael is also a registered electrical engineer, an active member of IEE of the Philippines, and a member of IEEE. He is the co-author of a technical paper entitled Optimization of Power Transformer Insertion Dry-Out Process using Dielectric Frequency Response CFR, which was published in November 2022. Over his 19 years of experience in transformer testing, relaying, and SCADA, Michael has contributed a lot to the electrical industry. He enjoys sharing his knowledge and experience through technical presentation and is always invited as guest speaker for many industry events. So now I'll pass the time to Michael. Thank you for joining us today. Michael, please.
Yep. Thank you so much, Grace, for the introduction, and good morning, everyone. So our topic for today is about the live streaming. Okay, live streaming of current and resistance while we do the insulation resistance test. So we have the following agenda. We will do the introduction first, talking about the principle, the theories, and then we will talk also about the different currents that you can see when you do the DC insulation resistance test. And then later on, I will show you a video on how to do it. And of course, lastly, we will do the interpretation of the graph that we acquired from the testing. Okay, so like I've said, the live streaming is an additional tool for the analysis. So when you do the insulation resistance test, it is better to look at the current, what is happening during the test. So this is available actually with our MIT models, with the diagnostic models, MIT 525, 1025, or even in the S1 models of Megger insulation tester. Now let's review first. When we do the insulation resistance testing, of course, we are dealing with the Ohm's law because this is a DC injection, right? Direct current injection. So since we are dealing with the Ohm's law, we have this formula here. Voltage is equals to current multiplied by the resistance, or the resistance. We are getting the resistance by voltage divided by the current. Now, as you all know, with the higher voltage that we have, we can have a better accuracy because, you know, the resistance is directly proportional with the voltage. So as the voltage go high, then we can measure a higher possible resistance, right? So the more test voltage that we have, or the higher test voltage that we have, we can have a higher resistance possible. Okay, so we all know that no insulation is perfect. We have some electricity that flows or leak along the insulation or through to ground. Such a current may only be a million of ampere, so sometimes we are dealing of a microamp here. And this leakage current, please take note, we are looking at the leakage current. This will be our basis for the insulation testing. Okay, so, and according to NETA 2019, if you look at the NETA standard, that is the ANSI standard 2019, these are the commonly used test voltage. So for example, here, when you have 250 volts equipment rating, then you need to test it by 500 volts DC. And as you can see, it's just almost double. So by the rule of thumb, we just double the voltage rating, and then that will be our test voltage in DC. And this is the recommended minimum insulation resistance here. So if you inject 500 volts DC, then at least you must have 25 mega ohm, and so on. So as you can see here with the new standard, if you are talking of 34,000 volts equipment rating, then you can test it by 5 kV, and then at least you must have 100,000 mega ohm value. That is the minimum. Okay, but of course that is just only a guide. So if we don't have a previous test result, then we can base our assessment through that guide or that table from the NETA standard. That is table 100.1 from the NETA standard. But still, the best way for me is by doing the trending analysis. Okay? But of course, if you do the trending, you need to make sure that you need to correct the value to a certain temperature. So for example, you got a result from 30 degrees, you measured a value at 30 degrees, and then you measure the value at 35 degrees. Of course, you need to correct it to some other reference temperature. So normally, when we talk of insulation resistance, we are correcting it to 40 degrees Celsius. Because remember, resistance has relation with temperature. Meaning to say, as the temperature changes, the resistance changes as well. So you cannot compare values at different temperature. You must have a reference point. You must have a reference temperature. And normally, when we have it, uh, when we have it corrected, we need to correct it to 40 degrees Celsius for the insulation resistance testing. So when you do the trending or when you do the comparison, it needs to be at the same temperature. So sometimes we do the correction, record and factor the relative humidity, because the higher the humidity is, it will also affect our result, because high humidity means you have a high moisture. It's almost cloudy if you have a high humidity. So some time interval for spot readings. Of course, you need to consider the time of your testing. Okay. Now let's review the current that we have when we do the DC insulation testing. I know you have seen this before, but this is very important with the live streaming. Okay. So first we have let's look at this insulation here. And of course, insulation, we normally treat it as a capacitor, right? So we have conductor on the other side, conductor on the right side, and we have the insulation in between. So that is capacitor here. And this insulation here is composed of dipoles, which has two charges, combined two charges, the negative and the positive. That's what we call the dipole. And we also have the electrons or the negative charge, right? Now, what will happen if we inject or we inject a AC voltage? So what will happen is that these electrons will move freely, just rotating, going anywhere, because we are injecting a voltage that is cyclic or cycling, positive, negative, positive, so it's oscillating. So no direction for the charges. The same thing that will happen on the dipoles. It's rotating anywhere, and they are just like dancing because it's at AC voltage. Now, what will happen if we inject a DC voltage here? Of course, that negative or that electron will be attracted to the positive test probe, okay, to the positive side. And we said, or we know, that once the charge moves, that is current. But remember, we are looking at the leakage current. And this current is not a leakage current. This is only a capacitive charging current. Okay, so when the electron moves towards the positive side, it is a capacitive charging current. The same thing happen at the same time is these dipoles aligned and uh, towards the opposite charge, towards the opposite polarity. So like in this one here, right, the negative towards the positive towards the negative. So it aligns. And again, that is a moving charges, right? That is a moving charge. So meaning that is also a current, and that is not a leakage current. We call it the absorption current. So it is happening at the same time, but it takes longer than the capacitive charging current. So what happened is that uh, you have the capacitive charging current, and at the same time, you have the absorption current happening in the first few seconds. Now here comes the conduction current. That is the current that we are looking for. The leakage current that is passing through our insulation when we inject the DC voltage. So that is the current that we are looking for. Okay, and sometimes if you have some contaminants on the surface that is not being tested, for example, the side of the bushings, then that is a surface leakage current. That is also happening if your test object is dirty or sometimes has some moisture outside. So that is the surface leakage current. So again, when we do the testing, when we do the DC injection, we have the capacitive charging current, which is happening in the first few seconds. We have the polarization current, which takes longer than the capacitive charging current, and we also have the leakage current through the surface of the test object. And this is the graph of the capacitive plus the absorption current, and adding the conduction current, that is the total current that we have. Okay. So with this illustration, guys, um, this is the reason why we normally do IR in 60 seconds. So meaning to say, we let the capacitive charging current and the absorption current happen first, and then we measure when it is gone. And that is estimatedly happens after 60 seconds. So we normally measure here at the end to make sure that we don't have the capacitive charging current, the absorption current anymore. And we are looking only or purely at the leakage current and the surface leakage current. But of course, you don't want to have the surface leakage because that is not the insulation that we are trying to analyze here. We are trying to analyze the insulation that has no surface leakage. Then how you can eliminate the surface leakage? So here in this slide here, that is the purpose of the guard. So in this example here, if we have a bushing, I'm just trying to analyze the resistance between this bushing to the tank, for example, or to the flange. So, but the problem is I have a surface leakage. Most probably this bushing has some dirt and it is wet, or there's some moisture on this side. So meaning there is a current that is flowing here, and that is the one that I wanted to analyze. However, there is also a current that is flowing here because of the surface leakage, right? So in total, you have two resistance in parallel. You have the resistance in the surface leakage and the resistance that you wanted to test. So meaning you have a parallel resistor, which is not supposed to be because I just wanted to analyze this resistance here. Okay, what will happen if you put the guard is that this surface leakage is diverted going to the guard terminal. So the same purpose as your security guard, if you have in your establishment, it doesn't want to allow anybody or anything to get inside because it's not it's not allowed. I mean, so meaning here, all the current that is passing to the surface leakage will be captured by the guard terminal, and it will be subtracted to the total current that is being measured, so that you can only have the pure resistive or the insulation resistance from the terminal to the tank of that bushing without the surface leakage. So meaning to say, if you put the guard, then uh, you can accurately measure the insulation resistance. But remember here, if you do the trending analysis, you need to make sure that if previous years or previous tests you did not put a guard, and then you put the guard here, you might get wonder why, oh, why my resistance got improved. Most probably because the previous test guard was not used. So every time you need to compare results, or if you do the trending analysis, you must do the same thing, and you know, so you can compare and you can analyze better. Okay, so that is the purpose of the guard here. So the current that is going to the surface leakage is diverted to the guard terminal and will be deducted to the total current measured by the insulation resistance. Okay, so now let's move on to the live streaming test. This is a short video on how you do the live streaming. This is very important when you do the testing, because sometimes there are some people asking me, sir, why we cannot test the cable with your IR? It's always displaying error, or sometimes it's always displaying an erratic or different values. Well, this is the answer. Okay, this is how you do it, or this is how you analyze why you cannot test that test object. All right. So let me play a video here. I hope you can hear it clearly. All right. Okay. So guys, I'm going to teach you on how to do a live streaming. While we do the insulation resistance test using the MIT 1525 here, and we will try to test this motor, small motor here. We are connected at the moment to the coil and to the ground. So my PC is connected via this white cable or USB cable here. So the first thing that you need to do is that you need to set this IR or installation resistance tester to acceptable. So this MIT 1525 has presets value from 1 pound times or twice the voltage rating of the motor. So this motor is rated 220 volts, or I mean, we can inject up to 500 volts. So here, as you can see, 100, and then select the IR, and then you can customize the test voltage here. So you can put 480 if you want, or I will do 500 volts, and then I click OK. So that's 500. That 500 will be seen in this voltage output here, right? You can see the voltage with the lock symbol, padlock symbol. So I will do the IRT so that I have 1 minute time. Okay. So now let's go to my screen and connect the PC to the IR. So need to open the Power DB, but before that I need to record the screen here. Windows R. So now, wait. I need to open the Power DB Lite first. And then I need to open the MIT.
1525. Where's that? This one. And then, of course, you need to check first what is the serial port of this connection, what is the serial port of the USB that the MIT is connected at. So you need to go to Device Manager, but of course, you need to install the driver, okay? You need to install the driver. So here, you can see at the COM port here. This time, I need to record the screen. All right, now it's recording. So I need to check the port here. As you can see, the Megger device is connected to COM6. So this is COM6. Okay. Now I have set it to the serial port number 6. I need to record it here. Sorry about that. So okay. Then I will open just the IR test. So in PowerDB, you can see a lot of templates here or forms that you can use in a specific test object. But at the moment, I'm just trying to use this IR test here. Okay. So now I have this form, and I'm ready to connect to the MIT. Okay. So as you can see here, we have selected 500 volts connected to the motor here. Then you can click anywhere onto this voltage or this one reading mega ohm. Just left click, and then it will open the form or this box here. So what you can do is to do the start live stream, and then it will give you some instruction. You need to, number one, you need to select the IRT and then select the test voltage. So in this case, I have selected the 500 volts, which we customized a while ago. And then now I'll just need to press the test button here. All right, so now as you can see, you can close this dialog box. So you can see in the screen the increasing value of current. Right? Well, actually, you can customize this Y and X axis information. Let's say you want to see the resistance, or you want to see the time for the X axis. Normally, it's the time. Or you can also go with the Y axis, resistance on the Y axis. But I already started, so I cannot change it anymore. So let's just wait for 60 seconds because the test is IRT and it has a default of 60 seconds, as I explained a while ago on how this current. So you can see here, this motor is displaying a very, very good insulation because there is no sign of abnormality. Meaning, of course, you have the high current from the start because it includes the capacitive current and the absorption current as well. So that's why it has the increasing current in the first few seconds. But after a while, capacitive current is gone, polarization current is gone, so will go down, so the resistance will go down as well. So here you can import these values to the form if you wanted to. So you can click Save Selected to Form, and it will automatically fill up the form. When you close this dialog box here, so as you can see here, I got the values up to 60 seconds, of course. Okay, so it will be very useful for you guys to analyze the current, especially if you have a highly capacitive test object. Then you can clearly see if it can be tested or not, because sometimes it cannot be tested because of the limitation of the test current we have. I mean, this current here, we have a limitation for for the insulation resistance. For example, if we are going to test a long cables, right? And we all know that cables is a highly capacitive test object. So sometimes we cannot charge this test object, and we cannot test with the IR. That's why we need the BLF, or a very low frequency tester. So here, with the live stream, the use of the live stream is that you can clearly see what is happening with the resistance or with the current. Okay, so let's try once more. Okay, so here, I'll start a new live stream. Again, select the IRT, step number 1 here, as you can see. Select the test voltage, the customized voltage here, and then press the button. Okay. You can actually save, or you can actually start to import the result while it's running. You can go back to form, or you can actually, you can also change the test name so that once it is saved, then you can import later on. So this is actually a testing of this motor here. And with the value of the resistance that we have, is very, very acceptable here. We have the 88,000. It's only 220 motor, so it's very acceptable. Okay, so that's it, guys. Hope. Oh, sorry. I missed to save to selected form. Okay. That's it. All right. So I hope I have gave you some information on how to do this thing.
Okay, guys, so that is the video that we made last week. So now let's go on to the interpretation of the graph. Okay, so how do you interpret this graph? So like I've said, the live streaming will be additional tool for you to analyze why you cannot test sometimes the test object or what is happening with the current. And sometimes you can clearly see if you have some abnormalities, most probably if you have some moisture, then you can clearly see, oh, this is what is happening. Most probably this is the situation. Okay, so this is an example here, a current graph. So you can see the y-axis is set into the current values and the x-axis to the time values. So this is an example of a normal insulation, right? So the first thing, or in the first few seconds, the capacitive current is happening. That is why the current is so high, because you have the capacitive current. And when the current is so high, of course, the resistance is low, right? And then at the same time, but with a much longer time, the polarization current is happening, or the absorption current, right? So with the conduction current, that is present all the time up to the 60 seconds. But since we are only looking, or we are only concerning to that current, that we record the value at the 60 seconds, and that is because we are only, or we just wanted to know only the conduction current. Okay, and with the leakage current, if no guard, then that current you have at 60 seconds, if you don't do the guarding, then you can have the additional current from the leakage current. Okay, and this is also the resistance graph of a normal insulation. So as you can see here from the start, the resistance is low because you have a lot of currents. You have the polarization, capacitive currents, right? And the same thing happened we record the resistance up to the point of the 60 seconds. Okay, so that is the normal insulation resistance graph or resistance graph, correct. Now, this is an example of contaminated insulation. So what you can see here, on the first few seconds, you can see that the current is getting high because you have the capacitive current, the absorption current, but as the time runs out, you can see that the current is still high. So meaning to say, or most probably, that insulation has contamination. Okay? Because the current is so high, it's not changing, it's not lowering down. And even when you look at the resistance graph here, you can see that the resistance is so low. So meaning to say, uh, that is a contaminated or most probably that insulation is already deteriorated, not a good insulation anymore. Okay, so this is the example of the resistance graph with contaminated insulation. Now, what will happen if you are trying to test a highly capacitive test object? The graph will, I don't have the sample, the exact sample um, graph, but this I have seen it before. This is how it looks like. So you can see the current is going up, going down, going up. So charge, discharge, charge, discharge. Because this is the highly capacitive test object, the MIT or the insulation resistance cannot charge the test object. So you must change your test equipment to a you know to a more dedicated instrument for specific test object. So for example, if it is cable and it is a very very long cable, maybe 1 kilometer length or more, I mean, you cannot use the insulation resistance anymore for that application because it is a highly capacitive test object. Now, to make sure that you can test or not, then you must do the live streaming and look at the graph. So in here, it is very obvious that my current is just charging, discharging, charging, discharging. It's not maintaining on a level that is measurable. So we cannot do the testing with that test object. So what you need to do is, use another dedicated test equipment like for cable or the Bellero frequency or the tangent delta tester. So you can use that one for that um, highly capacitive test object. But, I just want to explain more about the capacitance. Why we cannot do the why we cannot test the capacitance or highly capacitance test object. Remember in our school days, in our engineering, we have this formula for the capacitance, right? So for the current, we have the voltage divided by the XC. Okay? And for the capacitance, we have this formula, area over distance multiplied by the permittivity of free space. And if you are talking to a specific insulation material, then you have the relative permittivity or the electric constant of that insulation material. So capacitance will be this. Geometric capacitance, by the way, this is geometric capacitance. So geometric capacitance multiplied by relative permittivity. So the total current or capacitive currents that you can have, is the 2 pi f or the angular velocity multiplied by the voltage or the test voltage that you have, area over the distance multiplied by the permittivity of free space and the relative permittivity of the electric. Okay, so that is the capacitance formula. And when you do the DC electric field, when you inject DC, because we are doing the insulation at DC, you will see here that as the voltage increase, the current goes down. That is the normal. Uh, what is happening when you do the DC voltage DC injection. Okay. So looking at this formula, capacitance is multiplied by the relative permittivity multiplied by the free space permittivity, area over the distance. So remember, in the previous slide, we have the geometric capacitance, right? So this is permittivity of free space divided by the distance. And this is very useful, to get the capacitance value. So in most cases, the insulation resistance, you can also check the capacitance value. So maybe later on, or on the next webinar, I will discuss how to measure the capacitance using the insulation resistance testing. This is very important to look at the geometrical capacitance, because this will indicate if you have some deformation in your insulation. Remember that we have this formula, right? So if something happened with the area, for example, it has been dilapidated or it has been bended or something, then the capacitance will change, right? If the permittivity or the insulation got moisture or contaminated, the capacitance will change. If the distance here will change, probably it was deformed or something, then the capacitance will change. So when we do capacitance testing, meaning to say, we are looking at geometrical deformation of your test object. So you need to record the capacitance. And when you do capacitance testing, it is good to do the trending, right? It is good to do the trending because it will give you some information what is happening with the geometrical status of your insulation. So normally, the highly capacitive test objects are large rotating machines, large motors, large generators, and cables. Remember that when you have cable here, you have a conductor, right? This is a conductor of a cable. And then normally it has some sheet or shield, and this shield is a conductor as well. So why do you think this cable is highly capacitive? Because the area is big, so the capacitance will get high because area is big, right? And the distance is small. This is the distance, right? This is small. So as the cable gets longer, it gets higher capacitance. So sometimes we cannot do the test because we cannot charge this capacitance. And in order for you to check if you can test is by doing that live streaming there. And we have some limitation. Like I've said in the video, we have some limitation. You can check if that highly capacitive test object or if that test object can be tested with the IR tester. So you can compute, this is our maximum charging current, 3 milliamp, for example. That is a normal charging current for insulation tester, 3 milliamperes. So that you can compute. If you know the capacitance of the test object, then you can put the capacitance value here, multiplied by the test voltage that you wanted, and then multiplied by the 2 pi f, angular velocity. So meaning to say, in order for you to change the output, you can play with the voltage or the test voltage that you have. So you know the capacitance value, you know your test voltage, or you can adjust your test voltage. But remember, the maximum current that you can inject is only 3 milliampere. So you can check whether the test object can be tested or not by knowing the value of capacitance it has. Okay, so that is how to check the current limit. Okay, so I guess that's it, guys. I just wanted to share with you this, a very useful analysis tool, the live streaming. And for any additional information, you can download our guide to diagnostic insulation testing above 1 kV, this one here. And it is free to download from our Megger website. Okay, so I guess that's it, guys, and I'm ready to take some questions.
All right. Thank you, Michael, for your wonderful presentation. So now it comes to the Q&A session. If you have any questions, please type into the question box you can see on the left-hand side. And we read our questions one by one. And for those of you who are leaving, please have a fill in the survey, which you can see on the right-hand side. Your comments are very important for improvement. And after you finish the survey, you may download the attendance certificates, which you can see on the bottom control panel, which is the icon on the right-hand side. So, Michael, are you ready to take some questions now?
Yes, Grace, yes.
Okay. The first one question is if during a high voltage test, we perform IR before and after the high voltage test. What do we need to observe in the IR results before and IR results after?
During high voltage test, we perform IR before and after the high voltage test, right? What
Yes.
do we need to observe in the IR results before and IR results after? Yes, sir, you can use the live streaming that we have, observe the current and the resistance graph, as I explained in the video and in the slide. So you can clearly see if you can test the test object, what is happening, is it charging, or we cannot charge. So you can clearly see during the live streaming of the MIT or any insulation resistance test.
All right.
Okay.
And the next question is, for IR test voltage, is there a IEC standard that specifies what voltage to be applied on the test object?
To be honest, I'm not familiar with the IEC standard yet for DC insulation tester, but I have seen before. They also have some recommended standard, but for different test object. For example, for motor, you got the times 2 plus 1 kb. Uh, but for other, no, no, not times 2 plus 1 kb. I think it's around times multiplied by 3. But I'm not, sorry, sir. I'm not familiar yet with. I don't have specific standard for the insulation because insulation resistance has a lot of standard. But for IEC, it's higher than the ANSI. I'm pretty sure of that. The test voltage required by the IEC is higher than the ANSI. That's what I know. But yeah, we can get back to you on this. Let me check for the IEC standards for the insulation resistance, and then we will send it to you.
Okay. And the next question is, how to properly use the guard? Sorry, I'm just able to read the first set the first question.
What it's trying to ask here is that how to properly use the guard. Is it needed to put or to wrap around the body of the test object? And where should it be wrapped around? So insulation. Okay, so when you do the guarding, sir, okay, you need to analyze first, or you need to do the electric modeling. So let me share my screen again, Grace. I wanted to answer
Okay.
this one. Share. So probably I'll make a new blank slide here. Okay, but it needs to be white. Can you see my screen, Grace?
Yes, but
All
it's
right.
in black. Yeah, okay.
Now it's in white, right? Okay.
Yes, okay.
So what I'm trying to say here is that you need to do, or you need to learn the dielectric modeling. Dielectric modeling. Anyway, yeah, it's clear, right? So meaning to say, sir, if you wanted to test an object, you need to clearly identify the insulations that you're going to check or to test. Okay, so for example, I have a transformer. Okay, then I will draw the electric model of transformer. In a transformer, I have a I have a conductor, which is the primary winding. So I got the primary winding as my first conductor. I also have the secondary as my or the low voltage winding as my secondary, and my conductor number 2. So this is the low voltage. So looking at this diagram here, it is very clear that I have 3 insulation to test. This is the insulation between high to low, high to ground, and low to ground. Okay? So if I will inject voltage from high to ground or to tank, so I'll put the negative here, I'll put the positive here. then it is very clear that my current, my leakage current that I'm trying to look at will flow somewhere here. This is the main flow of current that I wanted to see. However, if you try to look at this, there will be some current moving here going towards the ground as well. So meaning to say my current is splitting up. So in order for me to measure what I wanted, which is the high to ground only, then I need to guard this one. The phase or the portion that I don't want to influence my calculation. So like in the bushing a while ago, right? A while ago. So if you have a bushing, right, and you wanted to test just the resistance between this terminal to tank and the insulation will be my bushing, then it is very clear that the current will flow here, and that is what I wanted to measure. However, if there is a surface leakage, then it will split up, right? There will be current going here as well, and that will result to a parallel resistance. That will result to parallel resistance, right? So it's very difficult to use the touchpad in drawing, making drawings. So I wanted to eliminate this current here. So what I need to do is to guard. Maybe if you don't have a semiconductor item or a belt, sometimes they call it a belt semiconductor, or guard a hot collar or something. So if you don't have that one, you can actually use a bare copper wire or any wire that is bare, a conductor. That is good. However, we are avoiding that one because sometimes it can damage the insulation or the insulator. It can scratch the insulation, but it is the the best material to use for guarding. You can use a bare conductor, and then you can have the guard here. So meaning to say the current that will flow here will be captured by the guard, and it will be deducted from the total current that you are trying to measure. So just analyze where the current is flowing. If you wanted to divert that current to guard, so that's how you connect the guard. Just connect the guard to the portion that current is flowing, which is not necessary or should not be included in the total computation of the resistance. Okay. All right. I hope that answers the question.
Yeah. Thank you, Michael. And the next question is, can you please explain again the use of guard on the Megger equipment, and in which case do we need the guard?
I guess that is the one I explained.
Okay. And the next is, if a cable insulation is rated at 1000 volt but used in 220 volt, do we need to test the IR at 500 or 1000 volt?
We need to use, or we need to consider the rating of the volt of the cable. We need to consider the rating of the cable from the standards. That I'm talking about the standards here, because when we do cable testing, we normally use the rating voltage or the rated voltage of the cable. But of course, if it fails, then because the application is only 200, that's why you are using a 1000 volts instead of 200. Okay. Yeah, only 1000 volts. Yeah, you can use the rating voltage to test the insulation of the cable. You need to use the rated voltage of the cable, not just the application. Okay. So that is from the standard.
Okay, thank you, Michael. And the next one is, how significant is humidity with IR testing? Can leakage current usually be guarded out in high humidity over 80% to 90%?
We normally do not test insulation for humidity above 80%. Because remember, when we do the test in a high humid area, this is what it is. If you have 100% humidity, what is that? what is happening when you have 100% humidity. If you have 100% humidity, then you almost have a cloud. You almost have a cloud. I mean, it looks like, you foggy day, a lot of fog. So that fog is already a moisture, and that will affect your insulation resistance. You will have a lot of surface leakage because you have a lot of moisture around you if you have a high humidity. That's why actually that is not the basis. We don't consider the humidity in the computation of the resistance. We don't consider humidity in the computation of the tangent delta or the IPF, but we need to indicate the humidity because that will help us analyze. Ah, yeah. For example, yeah, you have a failing value of insulation power factor because it is very humid. You have high moisture around you. Okay? So that is actually the effect of the humidity when you do the insulation testing. Not only for the DC insulation testing, but also on the insulation power factor. So we recommend not to test above 80% humidity because there will be a lot of moisture around you when you do the testing. And of course, it will be the results that you will have will be confusing. Is it really my insulation is failing or because of humidity? Because I have a lot of surface leakage. So
All right.
yeah, that was
Yeah,
it.
thank you, Michael. The next question is, how does Megger correct for temperature? Is this done through software or is there a formula to use in Excel?
We have some in the software in the Power DB, sir, for the temperature correction, but we don't have. I'm not sure. I'm not sure. Uh, is somebody here, or maybe somebody tried
Uh,
it from my group? Have you tried the correction factor zoom in the actual device? I'm sure we can do only the temperature correction in the Power DB, but I haven't tried it with the actual unit. Let me get back to you on that, sir. We will get back to you on that. But normally, as I have seen before, it's done in the in our software. When you import the result from that live streaming or from the device, when you import the result into our Power DB, then you can do the correction. We can do the correction. But I'm not
okay,
sure yet of the in the actual unit. Um, I mean, in the actual screen. I mean, the result in the actual screen is corrected or not. I'm not sure yet, but I will get back to you on that.
all right. And the next one is, where are the reference tables for humidity and temperature compensation for DCIR? Is it specific or for different test objects?
Where were the reference table for humidity and temperature compensation for the DCIR? Is it? I have seen it before, but it's not really a table. It's a statement. It's a statement of the humidity uh, and temperature. But I really need to check the sorry the number of the standard. But I really forgot the standard. But yeah, it's not really a table. It's a just a statement, I guess, if I'm not mistaken. Uh, there is a statement saying about the relative humidity or the humidity, I mean, and the temperature compensation. I will check, sir, and I will get. This is from what company? Sorry. Ergon Energy. Okay. I think this is from Philippines. Uh, just send your number, sir, and we will contact you about this reference table for humidity and temperature. Okay, but normally we base it as a generic standard. We base it from the NETA standard 2019. Okay.
Okay. And the next one is,
Oh,
I
we have a
think
lot
that's
of.
the statement. Oh, wait, the last question I have is, why there is why is there a need to use the positive probe connecting the ground instead of negative probe?
Okay. That will be a long explanation, but we still have time, Grace. Maybe 3 minutes.
Yes, that will be the last question. Yes.
All right. Okay. So let me share my screen again, guys. Can you see my screen again, Grace?
It's coming up
Okay.
again.
That is because of what we call electroendosmosis.
No, we cannot see your screen yet, Michael.
You cannot see?
No, not yet.
Window share. Is it? Now you can see?
Yep, it's coming up now. Oh, yes, we can see now.
Okay. So we normally for 100 years we are normally connecting the negative side to the high voltage side. So for example, if you are going to test a transformer, okay, so let me draw a transformer here. And for example, I have the primary winding, right? So if I'm trying to test a insulation between high voltage to tank or to ground, then I am connecting my negative to the high voltage side and positive here. Okay, this is because of what we call electroendosmosis. So this is actually only present in the old insulation that is made not later than 1970. So for insulation that was made before 1970, we need to properly do this. Connect the negative to the high voltage side and positive uh, to the low voltage side or to the ground or to the tank. Because this is what is happening. We have some electroendosmosis. So it was known that when you look at the moisture, moisture has a negative charge, right? Moisture. And we all know that moisture is some kind or in a form of water, liquid, right? Water. So look at this. If you connect negative here, this negative charge or the moisture will be attracted only to positive, right? So you don't have any issue when you are connected the positive here because it will go towards the ground, right? But what if you will connect the negative here? It will repel, right? This moisture will trying to go up, which is not, I mean, it will not get stable because of the gravity that we have. Because of the gravitational pull, moisture is trying to get up. If you put the positive here, because he is only attracted to the positive side, because he is a negative, it is a negatively charged. Moisture is a negative charge. But you don't have to worry anything about it, sir, because that is only made for insulations, which is, uh, before 1970, made before 1970. So I think it's very rare to see some insulations that was made before 1970. And that is the reason, sir. You can actually search what is the meaning of this, and that is the phenomenon called electroendosmosis. Because of that, we need to connect the negative to the high voltage side, and at the same time, the Megger is injecting at the negative side. Sorry, so meaning the negative side, positive. So we are injecting voltage negatively charged, negative side. Okay. Yes, Grace. I think I have answered it.
Okay, thank you, Michael. Thank you for all the questions and very meaningful and fruitful answers. So I
Yeah,
think
great questions, guys.
yeah, I think that will be the end of the webinar today. So let me make a announcement of our next webinar. So our next webinar will be on the 7th of March, which is her first day, and the topic will be overview of solar PV installation testing for safety and efficiency. The time is 10 o'clock in the morning, Hong Kong time. So if you're available, you can go to our website, www.megger.com/webinars to register for the webinar. And if you have any further questions after the webinar, you can send us email to ea.marketing@megger.com. So just as a final reminder, please have us fill in the survey and also download the attendance certificate before you close the webinar window. And we have to thank you again, Michael, for your presentation. Thank you also our panelists, Sumedi, Bernardo. We hope to see you again next Thursday. Thank you, everyone.
Thanks, everyone. Bye-bye.
Thanks, everyone. Bye-bye.
Thanks, Grace.
Bye-bye.